All right, the next couple of sections, sections 3, 4, and 3, 5, both deal with what is called optimization. So this will be optimization part 1, section 3, 5, optimization part 2. Optimization problems put into practice all that work we've been doing with finding maximum and minimum values of functions, right? So a lot of real world application stuff involving optimization, when you put this into the context of a function that describes a specific situation, and I want to know what the maximum value of that function is or what the minimum value of that function is. Like maximizing your profit or minimizing your costs or minimizing the amount of resources that you need to accomplish your task. So those types of things. So over these next couple of sections, we're going to talk about optimization. The next section is going to involve a lot of application type problems. We'll do a little bit of that in this section, but we're also going to touch base with the fundamentals as well in this section. So first, recall. Now, we have talked about two different types of extreme values, right, or our extrema, right, those maximum and minimum values. We spend most of our time talking about what we call the relative or local extreme values of our function, which are the maximum and minimum values of our function relative to the values around it, right? Or you look at just a small piece of the graph, and you're identifying the maximum and minimum value. Like we looked at those turning points on the graph of a function, right? Relative maximums and relative minimums, but it's only within a certain region. We also have, though we mentioned these, we didn't really do much with them yet. We also have these absolute, or also known as global extrema, values of our function, which are the absolute maximum and absolute minimum value over the entire domain of the function. Right? So instead of just looking at a piece of it and recognizing that there's a relative maximum min value within a certain little region, if I look at the entire function, does that function have an absolute or largest maximum value? Does it have an absolute smallest or minimum value over its entire domain? Now, finding our relative extrema, right? We used our first derivative, where we found our critical values, and then we checked to see the sign of our first derivative, positive or negative, to tell us if the function was increasing or decreasing. We also had that second derivative test that we mentioned. We didn't really, make use of it. We said it was an alternative. You remember, second derivative tells you about concavity, but if you find your critical value and then plug that into the second derivative, we could also use that to determine whether there was a relative max or relative min. So that's still in play, but I think for the most part we still just use the first derivative, because why bother with the second derivative if the first derivative is going to get the job done, right? But remember, there are still two different ways that you could find those. But this section we're going to focus more on now finding those absolute extrema, right? Those absolute maximums and minimums. So for an absolute extrema, it is helpful to a certain degree, and we always talk about this when we're talking about function values or behaviors of functions. Having an idea of what the graph of a function looks like, just based upon what we know about that type of function, is helpful in describing the function's behavior. And in a case like this, first of all, the question does the function even have an absolute maximum or an absolute minimum, let alone being able to find it? And based upon what I know about a function, certain types of functions just don't have them. You look at a linear function, that's a line. Those lines are either increasing or decreasing for the most part. There is no absolute maximum or absolute minimum for graphs or lines that look like that. Right? They're going to go off to infinity or negative infinity. Now, there is an exception here. If I do have a linear function whose graph is a horizontal line, what we call those constant functions, that function actually has an absolute max and an absolute min, and actually end up being the same thing, right? Because every function value there is the same. But that's kind of a unique situation. Most of your linear functions are either increasing or decreasing. There is no absolute max or absolute min, and there's no relative extrema either. Now, when you talk about a quadratic function, right, those are the graphs that are these parabolas. So, we know that those functions would obtain either an absolute max or an absolute min, depending upon which way the parabola opens, right? But that's just based upon what we know about the shape of that graph. Now, those are also relative maximum or minimum values, because that can be the same, Now, because there's a turning point on the graph of a quadratic function at that vertex. It's a relative minimum or it's a relative maximum. It's also the absolute minimum or absolute maximum of the function over its entire domain. So those can be the same. We'll talk more about that as we go forward. If you look at a cubic function, right, or more generally just an odd degree polynomial, and these are just a few examples of what those types of functions can look like. But notice, just like your linear function, eventually the graph is going to shoot off to either infinity or negative infinity. There is no absolute max, there is no absolute min. Right? Now there is, or there could be, a relative max or min, right? Because like that third one, we do have some turning points on this graph, right? But so there is a relative max, there is a relative min there, but there is no absolute max or absolute min over the entire domain of that function. A couple of other types of functions we talked a lot about: exponential functions, log functions. So just reminding you what the graphs of those look like. Exponential functions either are increasing or decreasing. Log functions have graphs that either look like this or like that. Again, there are no extreme values there. Right? There are no relative, there are no absolute maximum and minimum values for exponential log functions over their entire domain. Right? So, just based upon what we know about different types of functions. Right? So, first of all, is there a max or min, let alone can I find it? It just depends on the type of function, right? Obviously. Now, what if instead of looking at the entire function, right? Because we have so many of these functions that don't have extreme values, right? Whether they be relative or absolute. But what if we look at the graph or just a small portion of the function instead of its over the entire domain? I can guarantee you that if we only look at a very small portion or just a small region of the graph of that function, it's going to hit an absolute max and an absolute min in that interval. Right? Because if we're just going to cut it off, even if that happens to occur at the endpoints, I guarantee you there's going to be one. That's a little bit more relevant to real world type applications where, you're not always interested in the entire function, but just the function within a certain region or a certain interval. So this is what gives us what we call this extreme value theorem. Ink got a little smudge there. But this EVT, or the extreme value theorem, tells us that if f is a continuous function, we'll remind you about continuous, defined on a closed interval. By closed, we mean that we're including the endpoints. So I've got this interval from A to B, including those endpoints A and B. Then if f is continuous over that interval, then f has to have an absolute maximum and an absolute minimum value over that interval. Now remember, what does it mean to be continuous? We said basically that means when you're drawing the graph of the function, you put your pencil to paper and you draw the entire function or the entire graph without picking your pencil up. Right? And that was just kind of a workable definition of what it means for a graph to be continuous. So in order to guarantee that there is an absolute max and an absolute min in our interval, the function does have to be continuous in that interval. So if you look at like that first graph that I have, that's basically the shape of an exponential function. That was one of our exponential functions, increasing function. Now over its entire domain, right, we said there is no absolute max, there is no absolute min, because that graph does shoot off to infinity here. The graph does continue to get closer and closer to zero as you go off this way, but it never hits zero, right? It never hits a smallest value. So there is no absolute max, there is no absolute min. What if instead of looking at the entire function, though, we only look at this function over the interval from A to B? Right? So on that interval, the function does have an absolute maximum value. It's right here at B. It does have an absolute minimum value. It's right there at A. Now be careful in the wording here. I find this sometimes can be confusing if we're not careful on the language. Anytime we're talking about the value of the function, right, that's your y value. And then the x coordinate or the x value is the location of where that function value occurs. Right? So in other words, I would say that this function has an absolute maximum value of f of b, whatever that y value is. And that value occurs at x equals b. Right? So x is always giving us the location. The y value is giving us the value, right, or the function value. So then we do have an absolute minimum as well of f of a, that's the function value, and it's located at x equals a. All right? And so again, we're only considering the function between a and b, or again, also including those endpoints. If you look at the second graph, right, similarly, that would be kind of like like we said, our third degree or cubic polynomial type graph. Over its entire domain, there is no absolute max or absolute min, because this thing is shooting off to infinity, is shooting off to negative infinity. But again, if we only consider a portion of the graph, say between a and b, then again, this function does achieve, it does attain an absolute maximum value at b, and that value would be f of b, whatever that y value is. Now notice it also does achieve an absolute minimum, but that absolute minimum is located at c. So f of c is the absolute minimum value of that function, located at x equals c. But notice it's also a relative minimum, right? And that's what we mentioned earlier with the quadratics, the vertex. It's a relative minimum or relative max. It's also an absolute, right? So just by looking at those two, so I ask the question, right, fine. If I want to identify where a function or what the absolute maximum or absolute minimum value of a function is, where do I look for it? Where would I find them if they exist? Well, over that closed interval, so in the two examples that we had, we see that those could occur at the endpoints of the interval, as it did in the first one. It could also occur at one of our critical values, right? Because when we talk about that point cf of c, that's c value is a critical value for that function, right? That's where our derivative would be 0. So it makes these actually pretty easy to find, in that if I'm looking at a closed interval or a specific interval on the graph of our function, and I'm identifying over that interval an absolute maximum and absolute minimum value. Now again, because it's a closed interval, I guarantee you that there is an absolute max and there is an absolute min. Right? So where do I look for them? Right, so again, we have this continuity thing. So for a continuous function f on that closed interval a to b, we can find the absolute max and the absolute min values of f on that interval by first finding our derivative. Why do I find the derivative? So that I can find the critical values of f. And how do we find those critical values? Again, we set the derivative equal to 0, or we look to see where that derivative is undefined. So step 1 and 2 is all about finding the critical values. Then step 3, we find the values of our function at the endpoints of the interval, right? So we'll find f of a and f of b, and we'll also find the function value at each of those critical values that we found in step 2. And then after that, it's simply a matter of comparison, right? So we know that the max and min, if they occur, or not if, but when they occur in a closed interval, they can only occur at either the endpoints of the interval or at one of the critical values. So once we identify the critical values, then we'll just simply test the values of the function, find the endpoints, f of a, f of b, find the value of the function at the critical values, and then simply compare. Right, so step 4, the largest of those values found in step 3 is your absolute max, and the smallest is your absolute minimum value of the function on that interval. Now, do be careful, and I'll give you an example to show you what I mean here. But do, of course, make sure that the value that you identify as the absolute max or absolute min actually occurs within the specified interval. And that's mainly about step 2, because you could have a critical value that's not in the specified interval. Like if we back up to this second graph that we had looked at, right? I mean, this function has another critical value over here. Right, there's another turning point. There's another place on that graph where the derivative is 0. But that point is not in our interval between a and b. So I don't care about that in terms of my absolute max and absolute min over my interval from a to b. So again, I'll give you an example with that to remind you, but find your critical values, but I'm only interested in those that are actually in the specified interval. So for example, first just a couple of generic functions, and then we'll do a couple of applications. So we want to find the absolute max, find the absolute minimum value of each of the following functions over the specified interval. So for number 1, f of x equals 3 minus 2x minus 5x squared on the interval from negative 3 to 3. Right? So step 1, find our derivative. And again, this is a nice little power function, so power rule, negative 2 minus 10x. Find our critical values, setting that equal to 0, and I get x equals negative 1/5 as my critical value. And then we just plug in our critical value and each of the endpoints of the interval into our function. So f of negative 3 would give you negative 36. Now again, we're plugging that into the function because now we're interested in what is the function value at each of these points. So then f of 3 is negative 48. Plug in negative 1/5. F of negative 1/5 gives me 16/5. And then we simply compare these values. The largest is your absolute max. So we have an absolute maximum of 16/5. It's located at negative 1/5. Or also notice here we're saying that the absolute maximum occurs at this point. Right? We have an absolute minimum. The smallest value there is negative 48. So we do have an absolute minimum that occurs at the point 3, negative 48. Now again, just be careful of the way the question is worded. If we're asked for the absolute maximum or the absolute minimum value, that would be the y value. That would be the y coordinate of those points. If we want to know where that occurs, then you could either give the x coordinate, or as we've done here, you can give the entire point. Right? So I would say that f has an absolute maximum value of 16/5. It occurs at x equals negative 1/5, or at the point negative 1/5, 16/5. And then similarly for the absolute minimum. So yeah, it's just a matter of how the question is worded in terms of how we answer that. So be careful there. Number 2, another little polynomial. So again, nothing too dramatic in terms of finding our derivative. So we've got this function f of x on the interval from negative 1 to 0. So we find our derivative, again, power rule, 3x squared minus 2x minus 1. Find our critical values by setting the function equal to 0. And I factored it, and I found critical values of x equals negative 1/3. And I also found x equals 1 as a critical value. But then this goes back to what I said earlier. Notice 1 is not in our interval. We're only interested in the values of the function that lie between negative 1 and 0. So since 1 is not in that interval, I don't care about that value. It's a critical value of our function, but it's not going to give me any information about what happens in the interval from negative 1 to 0. So I'm only interested in negative 1/3 because that's the only critical value that falls within the specified interval. So then again, we evaluate the function at the endpoint. We find f of negative 1. We find f of 0. And again, I'm plugging those into the function. And we plug in negative 1/3 into our function. And we get approximately 3.19, right? 86 over 27. And as usual, on my math lab especially, just watch your directions. Do we want a fraction, or do we want to round or approximate to a certain number of place values? So it just depends on what we're asked for. And then we compare. So we do have, again, an absolute maximum at the point negative 1/3, 86 over 27. And we have an absolute minimum at the point negative 1/2. Right. Number 3, just to give us a different type of function, something a little more interesting. So there's a function f of x equals e to the x minus e to the 4x on the interval from negative 1 to 1. And so again, I start with my derivative. Now remember, our derivative of e to the x is e to the x. And then our chain rule, our derivative of e to the 4x would be e to the 4x times the derivative of that exponent, which is 4. But that again goes right back to those exponential growth and decay models that we were talking about previously. So e to the 4x has a derivative of 4 times e to the 4x. So then our critical value, setting it equal to 0. Now here what I did was I factored out e to the x. Right? And if you factor e to the x out of this equation or this expression, that leaves me with 1 minus 4e to the 3x. Right? Factoring out e to the x out of e to the 4x leaves me with e to the 3x. And then we'll set each of those factors equal to 0. Now this we've mentioned before. This is e to the x equals 0. Well, that's never going to happen because remember, e is a number, 2.72 approximately. It's a positive number raised to a power. It's always going to be positive. It'll never be 0. So that doesn't come into play. Now, the other factor, this 1 minus 4e to the 3x, setting that equal to 0, and we'll solve that exponential equation. All right, so I have 1 equals 4e to the 3x, and then I divided by 4 to isolate the exponential. And this goes back to all these tools that we've worked with previously. And then I converted it to its equivalent log equation. So base e, so natural log of 1/4 equals the exponent 3x. And then solving for x, we divided by 3. So I get x equals natural log of 1/4, all divided by 3. Now this would be the exact value of x, right? But I need to approximate that one for sure, because I need to make sure that it is actually in the interval in question, right? So we're asked to find the absolute max and min over the interval from -1 to 1, so I better make sure that any critical value that I find is actually in the interval. So that one is approximately -0.46, which is in our interval. Now, of course, just like with that previous problem, we could find critical values that are not in the interval requested, and nothing says that any of the critical values have to be in the interval requested. And so it just depends on what the specified interval is. Let's say, for example, in this case, if instead of -1 to 1, I was only interested in the interval from 0 to 1, then again, that critical value would not occur in my interval. I wouldn't care about that -0.46. And the only points I'd be interested in would be the endpoints of the interval. But in this case, right, so -0.46 is in the interval, so we plug in our endpoints, -1 and 1, and we plug in the critical value that we found, and we get approximately 0.47 there. So then our comparison, we do have an absolute maximum, which occurs at our point, -0.46, 0.47, that is the largest of those three values. And then the smallest, of course, would be the -51.88, which occurs at x equals 1. So at the point 1, -51.88 is our absolute minimum. And then there's our absolute maximum that we mentioned. Okay. So, yeah, I mean, this is not too difficult, I think, compared to some of the other things we've talked about. Definitely the applications always make things a little more interesting. But yeah, it's still nothing more than finding your derivative, finding the critical values. That's probably the most difficult part. Right? The absolute max and min thing is pretty straightforward, because once you find the CVs, then you're just plugging numbers into your function and comparing the values. But as I said when we started this section, there's a lot of real-world application for this stuff. Because when you're talking about application problems where you have functions involved, we're not always interested in the entire function. We're only interested in the part of the function that's relevant to the situation that we're dealing with. Right? So restricting of intervals is something that we typically do when dealing with applications. We just don't tend to think of it in those terms. But it's the same idea. Right? So I'm still just looking at the function over a portion of its domain. So like, for example, if you're calculating your weekly paycheck, so I have this function P of H. Calculate the weekly paycheck. I'm only interested in certain values of H. If we let H be the number of hours, right, I'm only interested in hours that were relevant to what I could possibly work during the week. So maybe something between 0 and 40 or whatever would be applicable to a specific situation, right? But that's a pretty basic observation. It's like, yeah, you're only going to work a certain number of hours, and there's only a realistic number of hours that could be worked within the week. Right? So we're limiting the domain. I don't care about P of 500, for example, right? Because I'm not going to work 500 hours in the week. Right? So that idea. So these next couple are more specific. Right? So I have a couple of functions and specific situations. But, we have the basics down. Now it's just as usual with applications, making sure I interpret the information correctly. I watch the language. Do I know what to do with it based upon the questions that is asked? So for number 4, we've got a function n of x, where x is between 0 and 300, where this function n is the number of units of an item that can be sold after spending X thousands of dollars on our advertising. We're asked to find the maximum number of units that can be sold and the amount that must be spent on advertising to achieve this, right? So, that's a realistic question to ask, right? What would I expect the maximum number of the item, right, or the product to be that I could sell? And then how much advertising do I need to do to achieve that maximum, right? But in an application, any time you have a question that asks you to find the maximum value or find the minimum value, it's all about optimization. It's all about that derivative. Right? So that's a pretty straightforward trigger. I want to find the maximum value of a function. I want to find the minimum value of a function. Start with your derivative, right? Because that's where the max and min could possibly occur at those critical values. And then we said also the endpoints of the specified interval. So we'll start with our derivative n prime of x. Now again, a nice little polynomial function. So n prime is negative 2x plus 300, setting that equal to 0. Solving for x, I get x equals 150. There's our critical value. So again, we plug in our endpoints of the interval, right? Because we said we're only interested in x between 0 and 300. Plug in 0, plug in 300, and plug in our critical value that we found. There's our maximum value, 22,506. Now applications, so make sure we're interpreting correctly what that means, what that tells me. So what was n? N was the number of units of the item that could be sold. What was x? X thousands of dollars spent on advertising. So n of 150 equals 22,506, means that we're selling a maximum number of units, 22,506. If, with x equal to 150, that's $150,000 spent on advertising. So as always, watch your units. What does x represent? What does the function calculate? Last one, number 5. Here we've got the dosage of x cubic centimeters, or x cc's, of a certain drug. The resulting blood pressure, B, in millimeters of mercury, so mmHg, is approximated by that function B of x, where x in this case is between 0 and 0.16 cc's. Question, find the maximum blood pressure and the dosage at which it occurs. Right, so again, question is find the maximum blood pressure. Automatically, I'm jumping on the derivative to get me started. Right, so I want my critical values. Again, this is, a polynomial function. Numbers are a little bit larger, but no big deal. Simple power rule, finding B prime. And I've got 61,000x minus 549,000x squared. Find my critical values, set that equal to 0. I went ahead and factored out the x. And then the other factor, and if you set this equal to 0, you will get approximately 0.11. I ran out of room down there, so I didn't write it. Right. But that is 61,000 minus 549,000x. Set equal to 0. Solve that, and you've got 0.11. The other factor, x equals 0. Right? So then we have our endpoints of the interval, 0 and 0.16. And then we have our critical value that we just found at 0.11. So we plug those into our function, give us our function values, and we're interested in, our question was to find the maximum blood pressure. That is what B calculates. There's our maximum blood pressure of 175.48 millimeters of mercury. And what amount of the drug? That's our X. That's the number of cc's, 0.11 cc's. So I've got a maximum blood pressure, 175.48. It should be, yeah. Millimeters of mercury when 0.11 cc's of the drug are administered. That's section 3.4.